Today we're going to move into chapter 12 as we continue our work with circles. Today our focus is going to be on what we call tangent lines, and we'll be able to use some properties of tangents to a circle to solve some problems. So on that very first page in your interactive notebook, that definition page, there is a piece for tangent. So a tangent to a circle is a line in the plane of the circle that intersects the circle in exactly one point, which we call the point of tangency. So I'll give you a minute to get that written in. So as you read that definition and then look at the diagram that you have in the center of your notes, where would we see a tangent in this diagram? Intersects a circle in exactly one point. Okay, so down here at the bottom, we have this line XM, which is our tangent. Okay? It intersects a circle in just that one point at point X. So that point X is called the point of tangency. Okay, the tangent is a line. So when you're asked to name the tangent, you need to name the line. We know from the very first unit to name a line, we use 2 points that are on the line with the line symbol. So line XM is that tangent. So our focus today is going to be on this tangent to a circle and some properties that we're going to talk about that will allow us then to solve problems. So if you flip ahead in your notes to a page we have not worked on yet before, we have two theorems that we're going to work with today. So on the left side, on the front, when you have it folded, you have this theorem that says, if a line is tangent to a circle, then it is perpendicular to the radius drawn to the point of tangency. So some pretty key words in that theorem. Okay? If a line is tangent to a circle, then it is perpendicular to the radius drawn to the point of tangency. So when I look at my diagram, my tangent line, I have a radius going to that point of tangency. This theorem is telling me that those are going to be perpendicular. Those are going to be perpendicular. The tangent and the radius drawn to that point of tangency is going to form a 90-degree angle. So that is going to be important to us. When you open up that flap, it again talks about that theorem. It says, in a plane, a line is tangent to a circle if and only if it is perpendicular to a radius drawn to the point of tangency. When you see those words, if and only if, that means that it works both directions. So if we have the tangent and the radius to that point of tangency, then we know it has to be perpendicular. The other way works too. If we know this is perpendicular, the radius and this line is perpendicular, then that line has to be a tangent line. So it works either way. So looking at the example inside, it says line. When I look to name this line, I have several options. We know from before, any two lines points on the line with the line symbol, or with this one, we also have this lowercase scripted letter. So we can use the word line with that scripted L to name the line. So either way, since they use the word line, I'm going to use that scripted L. So line L is tangent to circle S. Remember, we named circles using that center point, circle S, if and only if that line L is perpendicular to, we know it needs to be perpendicular to the radius. How am I going to name the radius? Okay, I can use TS or ST. It is a segment, so I must have the segment bar across the top.
Are we going to have to use that statement every time we answer that?
You're not going to be writing that statement, but that's what you need to be thinking every time, okay? If the tangent and the radius are perpendicular, tangent and the radius are going to be perpendicular. Okay? So, measure of angle STX is how much when I look at my diagram? It is 90. The point of tangency is what? Okay, point of tangency is that point T. Okay, so the line and the radius are going to be perpendicular if it's a tangent line. The other theorem says if two segments from the same exterior point, okay, so this is my exterior point, I have two segments from the same exterior point. Okay, if those two segments are tangent to the circle, which means they only touch the circle at one point, then they are congruent. So those two pieces have the same length. So again, when you open that up, they talk about that theorem again. If two segments from the same exterior points are tangent to a circle, then they are congruent. So they're just repeating that theorem. So again, we have an example. It says if segment QP and segment RP are tangent, means they're only intersecting at one point to a circle, then what do we know? Then they are congruent. So when I look at my diagram, I have a congruency statement to fill in. So what do I know to be congruent? Segment QP, so we need the segment bar, and segment RP are congruent. So now we're going to take a look at how we can apply those different theorems to solve some problems. So it says to use the diagram below, mine's off here to the left, to answer the following questions. And then they tell us that MC and MZ are tangents to the circle. Okay. So because I know that they are tangents, before we even start looking at particular information, because we know they're tangents, what does that first theorem allow us to mark in our diagram? Looking at your first theorem, if we know that MZ and MC are tangents, what can I mark in my picture? So where's my 90-degree angles? Okay. So angle Z and angle C. Okay. So those two are 90-degree angles. Okay. Looking at my theorem, the second theorem, what do I know to be true? What can I mark in my diagram? Okay. CM and ZM are congruent. So before I even look at anything else, I'm going to mark that in my picture because that's going to be true always because I have those two tangents. So number 1 wants me to find the measure of angle BCM. What is the measure of angle BCM? 90 degrees. We said that was a right angle. Those are perpendicular, so it's 90 degrees. Number 2 says to find the length of CM if CM is 5x minus 9 and MZ is x plus 7. So what am I going to do with that information? I'm going to set them equal to each other because those are the two segments that I know are congruent. So if 5x minus 9 is equal to x plus 7, I'm going to subtract x and get 4x. I'm going to add 9 to the other side to get 16. So then x is equal to 4. They want the length of CM. So I need to plug that back in. CM is 5 times 4, which is 20, minus 9, which is 11. If I plug 4 in for MZ, 4 plus 7 also gives me 11. Quick way to check, make sure I did my math correct. Number 3 says to find the length of EM. So EM is here in the center. Find the length of EM if CM is 12. CM is 12 and BC is 5. So how could I go about working with that? I kind of try to isolate that, okay, where I have this length of 12, a length of 5, and part of this. What do I have here? I've got a triangle. More specifically, I have a right triangle. So what can I use about right triangles that would help me solve this problem? Pythagorean theorem. Okay. If I use Pythagorean theorem, I can find this whole side, okay, MB. Okay. So I can use Pythagorean theorem. So 5 squared plus 12 squared is the hypotenuse squared. So I've got 25 and 144, which is 169 for C squared. So how much is C? 13. Okay. So 13 goes all the way from M to B. I only went from M to E. So how much do I have to take away?
5.
Okay, 5, because BC is 5, that's a radius, which means BE is also 5. So if I take 13 minus 5, then EM is going to equal 8. I'm going to get rid of that information in the picture so we can look at the next one. Number 4 says if the measure of angle CBM is 60 and CM is 13 square root of 3, find the length of BC. So how am I going to find the length of BC? Again, if I isolate that information, what do I have?
60, 30,
Okay, I have a 30, 60, 90 triangle. So this 13 square root of 3 that they gave me, is that the short, the long, or the hypotenuse? That's the long, it's opposite the 60. I'm looking for BC, is that the short or the hypotenuse? The short. So if the long is 13 square root of 3, what's the short in a 30, 60, 90 triangle?
13.
Okay, the short would be 13. Okay, because long equals short times square root of 3 in a 30, 60, 90 triangle. So if the long is 13 square root of 3, then the short, so BC, is equal to 13. Next one says find the length of CM. Find the length of CM if BC is 12 and BM is 20. So again, I'm looking at this right triangle, okay? This time it's not a special right triangle. I don't have any other angle measures, but I do know it's a right angle, which means I can use Pythagorean theorem again. So 12 squared plus, I'll call it b squared, equals 20 squared. Okay, just need to remember that 20 is your hypotenuse. So I have 144 and 400. So I subtract and get 256. So what is B? What is it? 16?
16.
Okay.
Sky.
So B is 16, which was CM. That's what we were looking for. And then the last one says to find the length of XE. XE. If BM is 25 and ZM is 20. So what am I going to do with this one? So that I can find XE. Hey guys, we need to be focused up here instead of messing around, please. What are we gonna do here? Okay. Again, I've got my triangle here. Okay. So I know these two sides. If I use Pythagorean theorem, I'm gonna find BZ. How is BZ going to help me?
Because it's the radius.
Okay. Because BZ is the radius, which doesn't change in my circle. Okay. So I'm going to say a squared plus 20 squared equals 25 squared. So I have 400 and what's 25 squared? 625. So I subtract 400, a squared is 225.
15.
So A is equal to 15. Okay. So BZ is 15, which means BE is 15, which means BX is 15. So how long is XE?
30.
XE is equal to 30. So, with those tangents to a circle, you see in a lot of this work we did here, we were working with right triangles. Okay. And we know lots of things previously about right triangles. We can use Pythagorean theorem. Sometimes we can use our special right triangles. So lots of information that we can get from that. So that finishes off this lesson.